So hello and welcome back. For lecture 5-2, we will do an example of using a discrete Bayes filter to find the probability of a robot being in a certain state where the state is represented by a location. So given a mobile robot represented by a 3x3 grid, where there's an equal probability of the robot being at any certain location in the world, and assume that the robot's pose is not relevant, we're only concerned with location. What is the posterior belief of being in each cell? And for this one, our input for our data is going to be a motion control command, whether velocity or based upon odometry based model. So the probability of being in a certain state xi in the world is given by the previous state. So we would have, for example, the probability of being in state x2 given u x1 would be 0.9 and so on. So all of the probabilities for going from one state to the next are given here, where some probabilities are 0. So for example, if the robot is in x1, we can assume that it cannot move diagonally, so it could only move to x2 or x4 and so on. So recall that Bayes filter and the model had a motion model, which is the probability of x given u, which is multiplied by the current belief. And that can either be discrete or continuous, which means either a summation or an integral. And then that is multiplied by the perception model, which is the probability of z given x, where n multiplies that value and is called the normalization constant to make sure it has a value of 1. So in the continuous time, the only closed form solution for this is represented by a Gaussian model. But in a discrete time system, like what we're about to solve, you can assume that this is a histogram that has a Gaussian shape. So it has bins that model the Gaussian distribution. So the algorithm to do this is given by the following. So assume that you have a function, discrete Bayes filter, that has an input that says, what is the probability of a posterior belief that I am in this state given this data point? So first I initialize my normalization constant to be a 0. And if my data is a perceptual data, such as z, then I have a for loop that says the next possible posterior belief state is based upon the probability of z given x given the current belief of x. And the normalization constant is equal to n plus the next posterior belief of x. And you do this for all x, so it ends up being a for loop. And then at the end, you cycle through the loop again and divide by n in order to get the normalization constant. Else, if d is an action item, u, where that's now going to be either velocity or motion control, we talked about there were two different ways to do that, then for all x, then the next posterior belief for that state is the summation over all x of the probability of x given u and the current state times the belief that it's in that current state. And then for this one, you can also return the belief for each posterior state. So what we're going to do here is we're going to calculate the probability of being in any cell in our 3x3 world, given the probabilities of being in each from the sensor data. So here we have our MATLAB script, where the first thing you see at the top here is the problem statement. Given a mobile robot in a world represented by a 3x3 grid, there is an equal probability that the robot is at any location in the world. That's our prior posterior belief. And we're going to assume that the robot's pose is not relevant. What is the belief that the robot is in each cell if we are now given a motion control input? So here our normalization constant is initialized to 0. The belief is 1/9 for every cell in the grid. And then we initialize our posterior belief after the motion control as BPS, and it's zeros, and it's a 3x3 grid. And then down here, I insert all of my possible probabilities based upon the robot's current location and where it's going to, where I'm calling the rows the from state and the columns the to state. So it's a 9x9 matrix. So for example, the probability that the robot goes from x1 to x2 is 0.9. The probability that the robot goes from x4 to x5 is 0.9. Or the probability that the robot goes from x6 to x3 is 0.1, and so on. So all of this was given in the problem statement. So first I'll run this section. And here we have our values of 0, 1/9 in our 3x3, and then all of our probabilities. In the next section, I'm going to implement that pseudocode that was in the lecture. So in this next section, I'm now going to find the probability or posterior belief that a robot is located in a certain cell in the world after being given the motion control as an input. So for I equals 1 to 3, for j equals 1 to 3, x equals I times 3 plus j minus 3, which converts that matrix into an index on our map location. So for example, if this is 1 comma 1, that becomes x1. Or if it's 3 comma 3, this becomes a 9. So for m equals 1 through 9, which represents all of our probability locations, I am going to write the value as that summation for the posterior belief I comma j, which is just the sum of I comma j plus I comma j times umx, where bij is our probabilities of being in any cell times the motion control given the from to cell. And so I sum all of those up, and then I find the normalization constant by summing up all the possible values for every cell and then dividing by that. So when I run this section, I get that the posterior beliefs of being in X1 is 0.0128, X2 0.1282, X3 is 0.1282, and so on. So the highest two values I have are X5 and X6. So I would say that the robot is most likely in X5 or X6, but still not completely localized until I have one value. So I would then use either a sensor input or motion control input and continue to move the robot through the world until it localizes. So this completes lecture 5-2 example on discrete Bayes filters. I hope you enjoy, and I hope you'll return again.